everyone. Thanks for joining us again. Up next, our next presenter is Jeff Abedisian. So Jeff has completed a Bachelor of Science in Biology from the University of Guelph in 2008 and has started as a water treatment operator in training in 2011. Since 2012, he has been supporting the piloting and hands-on training programs at the Waukegan Clean Water Center, both in the technician and scientist roles. He has recently completed a Master of Science in Environmental Sciences at the University of Guelph, where his research focused on microbial source tracking methods in Ontario waters. Since joining the water industry, finding innovative and practical solutions to protect source water quality and quantity is what he is most passionate about. Welcome, Jeff.
Thank you for that introduction, and good afternoon, everyone. For those of you in attendance who are unfamiliar or to the Waukegan Clean Water Center, or you're new to the industry, we're an agency of the Government of Ontario. We are best known for providing training and information, but we also conduct practical bench and pilot scale studies, mainly for small municipalities and First Nations communities. Earlier today, my colleague Helen gave a detailed summary of some of the available services that we provide. But typically we collaborate with consulting engineers, the operators and operating authorities on various types of water quality challenges. Today I'll be reporting the results from a case study that we conducted in Red Rock, Ontario. First, I'd like to thank the Red Rock operators, James Haskell and Pierre Dupuis, for their hard work supporting this project on site. Working with them was a great pleasure, and I'm thankful for the opportunity to get to know them. Thank you to Tricia Hamilton from OFNTSC, who collaborated with us and the Red Rock operators on this project, as well as Jeff Graham, Elliot Jones, and Suleiman Young, who are from the center, and they contributed a great deal to the project as far as the planning and execution. So the purpose of this project was to provide some strategies to reduce disinfection byproducts in the Red Rock Indian Band's drinking water supply. So the Red Rock Indian Band is located on the Lake Helen Reserve. It's a beautiful community in the northeast of Thunder Bay near Nipigon, Ontario. The water treatment plant serves a population of around 300 people on about 108 houses. And the source of the water comes from Mission Bay, which is in Lake Helen, and flows from Lake Nipigon, which is to the north, into Lake Superior to the south. The water treatment plant was built in 2008. It uses chemically assisted filtration. The Coagulant stern pack is a polyamine chloride that is used with the recommended dose between 2 and 10 milligrams per liter for this system. After the static mixer there, the water enters an upflow flocculation tank, then goes and carries over to the ultrafiltration membrane with no sedimentation, and the water is disinfected with chlorine or sodium hypochlorite at a dose of around 2.5 to 3 milligrams per liter. They have a large storage tank for fire protection, and their detention time varies between 8 and 10 days. So the community had disinfection byproducts, or DBPs, that were above the maximum acceptable concentration, MAC, and this was on and off since 2015, but consistently above the 2000 and in 2017 and in 2018. We were asked to conduct some bench scale and some pilot scale tests to see if we had any strategies that could help reduce the levels below the max. So first, we looked at completing a jar test, and we aimed to simulate their membrane plant as much as possible and see if we could remove organics using the coagulant that they had and playing around with the dose. We also looked at the potential impact of reducing the detention time of their storage tank and distribution system. And lastly, we piloted 2 GAC medias, a coal base and a coconut base as well. And we wanted to further reduce DBP precursors. And with that, we also monitored UV absorbance in real time to see if that would be a reliable indicator for to be able to predict disinfection byproducts in real time. So let's briefly look at some of our limitations before we get into it. There were some water quality and operational factors here that limited the efficacy of our possible solutions. So, for example, the alkalinity of this water was low. It was near the operational guideline. This is important because alkalinity is essential to form floc, and it's consumed in the coagulation and flocculation stages. So this limits the amount of effective coagulant that you can use, meaning that you can't simply just add more coagulant and expect to see better organic removal. Additionally, there's the operational limitation related to the dose. Ultrafiltration membranes have a narrow range of coagulant dose with their recommended amounts from the manufacturers. So the objective here is to get a pin floc rather than a full floc that's going to settle. So too much coagulant is going to increase membrane fouling, and that can certainly cause problems. Here they have colder water, which means that certain coagulants are just going to outperform other ones. And for example, we expect to see Sternpak outperforming alum, just as one example there. And the detention time, obviously, in this system is longer than what you would typically see for average, just because they have fire protection in a very small community. So they have to maintain a certain volume in that storage tank, and that limits what they can do, and they just have to work within that limitation. Lastly, the DOC is relatively high in this water source. It's around 5.8 here on average, but it got as high as 7.5 or so. Now, although the treatment appears to be performing quite well here, the treated DOC is still high considering that long detention time in their distribution system. With here, just a quick note, the raw pH historically was between 7 and 8.2. So now let's take a closer look at what our expected performance would be for the jar test. And Helen touched on this as well. There's a thing called specific ultraviolet absorbance, which is an operational indicator that can tell us a great deal of information about the water source. So using this formula here, UVA and DOC, you can find a SUVA value, and that SUVA value tells us the relative composition of the organics in that water, as well as the expected removal using the coagulant alum in this case. Now keep in mind, that's if we are optimizing coagulation for organic removal, otherwise known as enhanced coagulation. Now, because we're using Sternpak, we know that this typically yields better results than alum. And obviously, how much better is a case-by-case basis. But anecdotally, from my experience, I've seen between 10 and 15% better removal for DOC. Edswald and Tobiasen found that the SUVA value that you receive here gives a pretty good representation of the what to expect when using coagulation for DOC removal, and that's been adopted by the US EPA for their approach for TOC removal. So how does that translate to the full-scale operation? Well, here's a set of 4 grab samples where the SUVA values are between 2 and 2.6. Now, the data suggests that we should expect to see on the lower end of that 25 to 50% DOC removal if we were practicing enhanced coagulation and using alum. So the plant on average removed about 45%, give or take, of DOC using Sternpak, which is slightly better than the lower end of 25, maybe 30% or so. So to me, this suggests that the plant is operating at or near optimum for organic removal already. And this is followed up by the fact that they were already dosing 12 to 14 milligrams per liter, which is already above the maximum recommended dose by the manufacturer for their system. So we did conduct some jar tests, and here are the results. So This graph shows the relationship of DOC on the y-axis and the coagulant dose on the x-axis of just 2 coagulants that we trialed. So the bench scale DOC removal results are not as good as what you'd see in the full scale, since downscaling a membrane process has its own set of challenges for that. So we were, however, able to get a good idea of where the limits of performance are for coagulation. And the coagulant doses along the x-axis, they're displayed as active ingredient or the equivalent, just to keep things simple. The data here shows that Sternpak is apparently optimal for organic removal around 20 milligrams per liter, and the Ferry Plus was around 30 milligrams per liter. We used aluminum residual tests to help confirm that our apparent optimal for Sternpak was 20 milligrams per liter. So this graph shows the aluminum residual on the y-axis and the coagulant dose for Sternpak on the x-axis. And this graph models the theoretical trend that you would expect to see with coagulation, where an underdose or an overdose has higher aluminum residuals, and the optimum is somewhere at the bottom there for the residual after it's being filtered. We did the same thing for the Ferry Plus using iron residual to confirm that apparent optimal for Ferry Plus at 30 milligrams per liter. So here we conducted a simulated distribution system, SDS, disinfection byproduct test, or DBP test. And this is of the March sample. And we had 3 sources: the full-scale plant that was treated but not chlorinated. And we compared that in parallel to the maximum recommended dose of 10 milligrams per liter and our apparent optimum dose from the jar test results. We completed the tests for 6, 8, and 10-day detention times, and we measured HAAs and THMs. So for this set of samples, all the sources, the coagulant doses, and the detention times had HAAs below the max, and the full-scale plant dose had 14 milligrams per liter at the time, and it was over the MAC for THMs at 8 and 10 days, you can see highlighted in red, but below for 6 days. Now, the actual 2017 and 2018 annual averages were 115 and 118 micrograms per liter, respectively. Therefore, these simulated distribution system results, they represent the actual system quite well. It's fairly close. Now, the jar tests indicated that increasing the dose of coagulant from the recommended to the apparent optimal could reduce DBPs below the MAC. Also, reducing the detention time would further reduce the DBPs. And interestingly here, the Ferry Plus apparent optimal reduced the DBPs to about half the MAC. Now, the one caveat observation that we had with the Ferry Plus was that it seemed to clog our filters on the bench scale tests sooner than the other coagulant Sternpak. And unfortunately, iron-based coagulants, they're not recommended for membrane filters. But I included these results because it's a promising result for other northern communities that have similar water qualities, and they have limitations, as well as they struggle with organics and DBPs. So this is potentially an opportunity for some systems and some communities out there where they may look to a ferric-based coagulant going forward. So now I'm going to move to the pilot results here. This is a scatter plot that shows the granular activated carbon filter performance and how we applied our real-time monitoring to estimate performance of the filters going forward. So I'm going to walk through this graph because it's quite busy. You'll notice on the y-axis, you've got DOC in milligrams per liter, and along the x-axis, you have UV absorbance. We have plotted various points throughout the treatment process, and that's including the raw in purple. You've got the water treatment plant effluent in green, as well as the 2 carbon filters in red and blue. The diamond markers here are the actual grab samples that were measured and plotted for DOC and UVA. We also conducted 8-day SDS DBP tests and have the results for the water treatment plant, GAC1 and GAC2, which aren't really on this graph. But the dashed green box highlights the lowest SDS DBP result from the full-scale plant. And you can see the values there where THMs are above the MAC and the HAAs are just below that threshold. The dashed blue box highlights the DBP result from the GAC filter samples, which were both under the max as indicated there. So with regard to GAC performance, both of these filters that we used were able to reduce DBPs below their respective max, and the coal-based GAC filter 1 outperformed the other coconut-based filter during our experiment at that time period with the SDS DBP experiments. With regards to the real-time monitoring, we created a line of best fit using the DOC and the UVA grab samples that were represented by the diamond markers. And the formula for that line you can see on the graph, y equals, with an R-squared value that shows the relationship is fairly reliable. It's 0.988. So we used UVA values from a continuous monitor, and we substituted them periodically for X in that line of best fit equation to predict DOC, and that's illustrated by the circle markers and labeled as estimates in the legend. You can notice that they're all on that line of best fit. So we created a dashed red line that you have there, and that's formed as an operational indicator to estimate the threshold of UVA as a potential indicator of DBP levels that are near the MAC. And we did this because DOC, THMs, and HAAs, they're all tests that have to be sent out to an accredited lab, and they're time consuming and time sensitive often. So the UVA indicator could estimate DBPs in real time with some reasonable reliability. So I would suggest if you're using this application or in this application, if the UVA value goes beyond that threshold of approximately 0.04, this would either trigger a sample for water quality or performance, or you take another look to confirm the operation of the plant is functioning as desired. For example, there's 2 estimated points there that are the right of the threshold, and that both of those may need further validation. So this may include taking a grab sample to confirm the UVA in a manual method, or maybe testing DOC at the time. You could check the water quality at other locations in the treatment, the filter runtime, or the dose of the coagulant as some checks, for example. So this threshold here, this value is likely to fluctuate a little bit seasonally in this case, but definitely would change depending on that water source. So some of our key findings here, the apparent optimum dose in this case for organic removal with stern pack was higher than what was recommended as the maximum for operational for the membrane filters. So operations had to look to slowly increase that dose of stern pack to find a maximum that didn't foul the membranes too quickly. Interestingly, the Ferry Plus could be a good coagulant for other northern communities that have DBP issues or high organics. Reducing the detention time reduced DBPs and often below the MAC, and adding GAC filtration reduced DBPs below the MAC, as well as UVA monitoring appeared to be a reliable and effective operational indicator that could be implemented if they chose to. And in summary, there were several strategies that could be implemented to reduce DBPs. Not all of them may have been feasible for them, And one strategy may not have been effective enough by itself, but a combination of multiple strategies is expected to yield better results and get their DBPs below the max. Lastly, just wanted to thank everyone again for your attention, and also to OWWA team for hosting this impressive virtual conference. It's exceeded my expectations for sure. And I guess now we can open up the floor for questions and comments. If there's anything I can't answer in the next few minutes, you can send me a text or I guess email me at the address below. Thank you.
Great, thank you, Jeff. Thanks for taking the time to speak with us. So if anyone has a question that they have for Jeff, please submit it into the chat box. There's not currently any right now, but we'll give it a few minutes. We do still have a few minutes left in the session. Let's see if any questions come in.
Okay.
If there's any questions, you can just submit it into the public session chat box just to the right of your screen. Just another minute in case anyone else is typing, but nothing has come in yet. Well, I think that's a good sign when there's not any questions to be answered.
Right. Okay.
All right. So
well,
if
thank you all for your time.
No problem. Thanks, Jeff.